Hello, everybody. I see everybody left to go for dinner, so this must be the real crowd here, right? Okay, so let me go ahead and start, and let me point out a couple things. Solar. So this is me. America should be working. Aha. So this is me at one end of the beach, and I'm going to take you all the way to the other end of the beach where I was running yesterday. And the idea is, how do you actually make thermosolar useful and make money, or can it even? That's the hypothesis. So let's first start with why we have to do this. The previous panel was talking about the need for energy transition because we have a huge problem with climate change. And humans do this now and then. I want to point out that about a century ago, the prediction was made for the end of civilization as we know it because cities relied on horses to move people and goods. And there was so much horse manure that the cities were ceasing to function. So I call it the manure apocalypse. Right now we have a CO2 apocalypse. And what happened was technology came to the rescue, right? The technology that rescued us from this terrible mess was cars. It produced a new terrible mess. But the hypothesis is we can fix that with technology. The first thing is solar. Solar is the most wonderful thing on the planet. It's a very good thing for photovoltaics, except if you take all this wonderful green land and now you cover it with solar cells to fix the problem, we're going to have a new apocalypse, I think, the silicon apocalypse. And one of the reasons is that if we take the good flat land for solar, how do we eat? And this is being manifested in places like Hawaii, actually. So let's keep going with what else can we do? And these are some of our alternatives we are going to explore. Now, I want to point out that the costs keep dropping for conventional photovoltaics. I just came back from Shanghai. A friend of mine there has opened a new factory. It's a 60,000 square meter factory, 5 stories. And on the roof of the building there, they put in solar photovoltaic. The return on investment is 3 to 4 years. So let's look at this real quick here. You have 3 options with conventional solar. One thing to note is if you do fixed position, you get about 24% efficiency. If you have one axis tilting, right, you will add about 15% to the total of amount of kilowatt hours you can generate. And if you have 2 axis tilt, you add about 25% to the average kilowatt hours per day that can be achieved. That is not an increase in efficiency of the panel. This is just realizing that when you have a panel in one direction, as the sun moves, it doesn't get so much light. So the question really is about the return on investment in money. If you have not much space, then you want to do this. The hypothesis is that solar thermal, I would contend, is not so much about concentrating sunlight to make heat, but by using the sunlight and the warmth from the sun to grow crops better. This is a very old idea. I actually read about this idea when I was a young person in school, almost 40 years ago, by the way. It was an article in Business Week about some farmers in Brazil who discovered that crops that are spicy, very high value crops, grow better in the shade like they knew that coffee does. And that these farmers back then were using photovoltaic panels to operate their farm. I have to go and find the article. I have not been able to find it. So that's everybody here's homework, see how far back that was. And I have friends in Hawaii where I like to go who raise coffee, and they normally raise their coffee plants or various other fruit trees, including papaya trees. And so they are now starting to grow their coffee solar panels. So this really is going to be the future, I believe, of solar power and high value farming. But let's explore this a little more, what this means. First of all, much farming is done using center pivot irrigation. And this is what it looks like. And what happens here is there's an arm that rotates around in a circle, and as it rotates around in a circle, it irrigates the crops. The next use of solar thermal is going to be in desalinating water. It can be very helpful for desalinating water, and then that desalinated water is then what is then get pumped to use for irrigating crops. So that is a very, I think, the better use of solar thermal than to try to make it in a minute for making electricity. Now let's look at the numbers, because being an MIT professor, I have to do numbers. I can't just talk about philosophy. So this is the land currently that in Brazil I find, and I provide the references here, and then we will be providing the slides for people to have later. That is center pivot irrigated, and it's actually all quite good for solar energy too. And there's about 33,000 of these circles in Brazil now. So if I look at the total land area, the area per machine, and the circle is about 900 meters in diameter. That's about as big as you can go. That's an optimal design for the pumping and the structure. That you end up with a very interesting thing, that if I allow about 20 meters per roads between the edges of the circles, we end up with about 90 hectares of land at the center pivot. What does that mean? It means that if at the center pivot on the vertices, I put a wind turbine, and then in the land that is not covered by irrigation, I put photovoltaics, and only 50% coverage. Look at these numbers. They're really quite amazing. We could have, if we only took half of this land, we could generate a total of almost 75 gigawatts average 24/7 power, which is about 25% of your current total Brazilian generation of electricity on a daily basis. The numbers are really quite big. Now, why would a farmer want to do this? Farmer may want to do this, and I have an error here. There's a 10 missing. A farmer could say, wow, for my center pivot field, which has those 90 hectares, I could generate $61,000 a year in income from the electricity generated. In other words, the farmer could generate as much, if not more money by electricity than by growing the crop. So you could essentially take the land you have now and not slow down the production of agriculture, but double the value of income from the land by building solar and wind. And remember, the solar thermal, its proper place is near the coastline to desalinate and then send that water inland to use on these crops. That's the hypothesis, and the numbers seem to make good sense. So now, let's looking about what is actually happening with agrivoltaics in Brazil. And here, written by some academics here, is a very good paper in Applied Energy. It came out in 2024 about this evaluation of the potential of agrivoltaics. And what they are doing in this paper is just the photovoltaic part. My hypothesis, and I'm in the process of contacting these people, let's add in the wind, because Brazil is a wonderful country and you have really smart people, but I don't think you have figured out how to make solar work at night either. This is why the wind is so important, because unlike today is a very bad day for solar. It's a great day for wind. That's why we need both, because the energy transmission needs diversity, not only in the people that are going to help deliver it, as we heard from an earlier panel. There needs to be the social, the ESG part of what we do with renewables. There has to be the same thing applied to the physics. So let's see where other places where the solar power thermal is important. The next big thing is Brazil is doing a fantastic job with what solar thermal should do, which is hot water. You have this law here that mandates that you have to install solar water heaters in these areas. So bravo, Brazil. And if I go online and I say I'm in Brazil, which I was, what can I buy? It turns out that it's very economical to buy solar hot water heaters. So distributed small solar thermal is absolutely the way to go for huge impact. And it needs to be more. But now I ask the question, look at all these. These are great. Where are they made? Okay. And the next thing I want to point out, the physics. These work really good, even if they're a little bit dirty. They're okay. So put this here, and we're going to use this at the end of the talk in a very interesting way about where they're made. Some are made here, but most are made overseas. So let's on the academic world. Often when people hear solar thermal, they think of solar thermal associated with gathering the heat and making electricity. The most common is parabolic troughs, typically in desert areas. Brazil has good hot desert areas. I would contend that they should actually be turned into irrigated areas. But if you were to do these parabolic troughs, here is the problem. A parabolic trough, which is the most common, only heats up an oil to about 400 degrees C, which is not useful from a potential of running a thermal steam plant. You have to burn lots of natural gas to get the temperature up to the mid 500s, which is what you need for an efficient steam turbine. The other problem is that these troughs have to be kept clean, because even if they're a little bit dirty, the efficiency drops very much, and then you're back to burning a lot of natural gas. So I've been to various ones of these plants, and when I talk to the plant operator, they say, yes, it looks good that we're doing solar thermal. Solar thermal is nice because we can store some energy for night, but, I still have to burn a lot of natural gas. The next thing is what's called a power tower, and this was pioneered by Abengoa in Spain, and they're much better. It's a field of 2-axis heliostats that focus the light to a single point. It's on the other side here. It's very bright, and you can get much higher temperatures, up to 500 degrees. And with this, you burn a little bit of gas, but you still need to burn gas when it's cloudy or the heliostats get dirty. These machines have the interesting point that birds like to fly toward the light for some reason. And when birds get up to about here, it's like a mosquito fryer, and they go, and the bird vaporizes, little parts drop. The giant mosquito killer kind of thing. Now, we tried to get around that problem. Oh, not see what happened. It stopped working. Okay, maybe I can get some help to the next slide, because I think the battery is dead. There we go. See if this works. Yeah, okay, so this is called a beam down tower. And this is some research we did with Masdar University in the United Arab Emirates. And these This was an old machine that was built originally by some Japanese researchers. The heliostats focus the light up here to another mirror, which then shines it downward to a receiver. And what we're doing research on is making it more efficient. And we did that by what is called the final optical element. And we then went to the receiver, which in previous attempts of power towers is a very sensitive device that is easily damaged. We decided to beam the light directly onto salt, hot salt. And by directly illuminating the salt, we could melt the salt, and the salt, you can't hurt molten salt. And then you store the molten salt, and we then could go to very high temperatures that was good for, we did not have to burn natural gas. And they had no pumps. Power towers need quite elaborate pumping systems. Power towers need, salt has to be pumped up high and then come down, and at night the salt and all of those circuits need to be kept liquid, so now you have to have electric heaters, and it gets very complex. So we eliminated that by just having the salt in a big giant tank at the bottom. That was the hypothesis, and this is how it works. This final optical element does a very fine focusing, so it goes through a small aperture and melts the salt. And then we have this divider plate that moves up and down, so you heat all the salt, and then as you're drawing the salt off for the heat exchanger, the cold salt comes in the bottom. The plate moves up and down. This is the divider plate. You can guess who this is. And this was my doctoral student at the time, and here we are building it. This is looking up from the final optical element. This is the salt. Let's see if I can play the video. There we go. So this is operating during the day. The melting of the salt, you see it bubbling away. It's not actually boiling. Those are convection currents within it, disrupting the surface. So we ran it very successfully for many months, and we then would draw the heat off through the heat exchanger, and so the system works. Very successful. The problem is photovoltaic cost keeps coming down so much. Battery costs keep coming down. So if you ask me today, Professor Slocum, you did this system. It was brilliant. It worked. It did what you said it would do. I would say yes. It was competitive maybe 5-6 years ago with batteries and photovoltaics. No longer. So I'm the first to admit it when it's okay. It was great success, but too expensive because its cost can't come down anymore. So in general, what else can you do with solar thermal? So this is a very interesting combination of photovoltaics with temperature. And what it is that multi-junction cells can be 50% more efficient than a single junction cell. And this is a company in Australia called Raygen. And what they do, it's very interesting. They take these very special solar cells, which are known, this is for examples of what are used in spacecraft, and they take all of the light energy, and including in the infrared, and convert it to electricity. But in so doing, they get very hot. So you can generate from this solar cell here that's the size of a person's hand, if you can put enough solar power on it, 2.5 kilowatts of electricity from this little, it's 10 centimeters by 10 centimeters, and you also get 5 kilowatts of heat. But you got to get the heat out. So what they do is they have their receiver here at the top of the tower. These heliostats focus the energy up, and they generate quite a lot of electricity, but then they also circulate water to take the heat out. And so this is what their plant looks like. That this big square here, this is for the water that they're going to heat up to cool the backside. And then they're going to use that hot water for a Rankine cycle. But the most interesting thing that they believe they can do, and they're building and testing the systems, is when you have excess electricity on the grid, take that excess electricity and run it through a heat pump to cool some of the water to make it very cold. So now when you want to have electricity out, you have cold water from the heat pump you used earlier, and you also have hot water from when you were running your solar cell. And now you've got a big enough temperature difference between the hot water and the cold water to efficiently run a Rankine cycle engine. And so that's what they do. And so that's where they call it PV Ultra. In other words, the maximum efficiency solar cell possible. And then you have the thermal hydro, where, remember, during the day when you have had excess electricity, you cool water and you also heat water, and you keep the two separate. And then you run the Rankine cycle engine. The net result is they believe that they get close to a system efficiency of almost 70%, which competes with combined cycle natural gas or actually pump storage hydro. So that's the plan. Now the challenge will now be to get the cost down. So the cost is still too high for large scale implementation. And the plan, though, is as you make more and more systems, they can bring the cost down. I don't have an opinion yet how low it can go, but it does offer a plausible alternative for what we would call a solar thermal hydro. And so that's what's happening. So I will be next week actually in Australia at this particular place. It's called Car Warp. And my goal going there is to do a detailed assessment and analysis of all the systems and see if I can help them drive the cost down. Because that's one of the things I do as part of my research is work with companies, do a total assessment of a system, and how do we get cost out. Okay. Now, the nice thing is the system itself, these mirrors, and now they're facing downward. It's makes a good picture. Normally, the mirror would be facing upward. And why the reason it's facing downward, so you can see this is what the heliostat looks like. And if you were having a bad storm come through, they get hail sometimes in location. You would point the mirrors downward so they don't break. And I added the picture of the sheep here. That's one of the things you do as you graze. So this is how they make their high temperature, low temperature. You dig in the ground a pyramidal shape, and then you use what's called a thermocline to separate the hot water on the top from the cold water on the bottom. And that's very standard technology. And land use, and now, I went too fast. I got to go back. Okay, so their hypothesis is that you actually have colder ground by using their system, so it's better for agrivoltaics, and that they believe that they will be able to, they have the same power density about as photovoltaics, but that you will have, because you have lower temperature at the ground, you will have better use of the agrivoltaics, and you have storage built in. That's the operating hypothesis. And it, like I said, they should be able to make this economical. Now, let's talk about policy. And I don't know who was here earlier of the earlier panel that I was listening to. And again, the social aspects. And I would contend that China has done a very interesting thing. And this is not, I find this here's my reference from the Climate Council, that China is an interesting world leader in wind and solar energy production. And let's ask why. Well, the real thing is this. So this is my friend Yang. Here's the person who just put in this. The building is being built. That's why you can see all the junk on the roof, because they're still building it. And The government in China has told all the business people, when you build a new building, if your roof is over 1,000 square meters, you will have solar PV on the roof, period. It's the law. And I asked her, why are you happy? And she said, originally I was not happy because my business is to make car parts. I am not a power person. Why are they doing this to me? Oh, but I have to do it. So as a business person, she dives in and she said, wow, I was shocked. I was amazed because the return on investment is 3 to 5 years, which is really very good for a big public works type energy project. And as a matter of fact, in China, she pays, and you have to negotiate. So she went to the power people, and for her roof, it's 1 megawatt of solar peak. It's amazing how big the array is on her roof. But remember, these panels are almost 25% efficient. So she paid 25 cents, American dollars, per installed watt, which is amazing. That's $250 per kilowatt. Very cheap. And why is it so cheap? Because in China, is it the labor is so cheap? No, 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 no. All these panels, when they make them, it's almost fully automated. There's some labor, but most of the factory, it's run by robots. They invested for the long term to make panels really inexpensive so they could have more solar power. Why? Well, China doesn't have a lot of oil. It has to import most of its hydrocarbons. It has to import most of its coal. It makes a lot domestically, but they said long term, we can't survive unless we're on renewables, period. And yes, it's nice that it cleans up the climate and all this other stuff, but fundamentally, for an economic reason, you have to have solar and wind. So I would contend that Brazil is doing really good. What, 80% or more of your energy is green or low carbon. But if you want to fully decarbonize, that means all those cars out there that are burning gasoline and have to stop. They have to be electric. So you will need almost 4 times as much electricity to fully decarbonize, stop burning. So you'll have to produce almost a gigawatt of power on a daily basis. You've got to go by a factor of 4. And it was very interesting. You've had this law that says the oil and gas industry has to spend 1% on research and development. But it was only recently, is my understanding, that this new bill came out that said you have to have some of it on renewables, the oil and gas and renewable energy. This is my understanding, that the more recent bill adds a little bit of detail. So I contend that and the new tax incentives you have for more solar and wind, it's really setting the stage for your government has done a nice job, a really good job of, okay, let's do more. And now I want to cycle back to the agrivoltaics. There's the opportunity to spend that money very efficiently and also help your farmers. If you help your farmers, then you're also doing better for social equity, because you have quite a few people now who are farming that don't make that much money, but now they can make a lot more money, which means they could have better money to spend on education and cars, and it really would help. Where have I heard that story before? Well, I have a poem here, and I'm only going to read the first stanza, and then there's a bunch of it in between, that maybe you can get some local artists to put music to this. This is the coupling of things, because you have to change the social dynamic of everyday people have got to want to dance to the music of the actual, maybe musically made, but to the music of embracing renewables. Okay, so think about it. And let me ask, every time I write these poems, I write all these. This is not Chat GPT. You could try to get AI to write it, but my poems, I put hidden messages or Easter eggs into them. Anybody plays video games, Easter eggs. And all my Easter eggs and hidden messages are nice. I don't have any bad ones in here, by the way. And the important thing is when I write the poem, The first Easter egg I want you to note that ChatGPT does not know how to do, maybe one day, is it has a shape. Like it has a nice shape. You got to get into the groove, baby. And of course, I've got Brazilian colors, green and gold, right? So that's important. And here's another Easter egg. Why do I say MCC? Are those Roman numerals for a number? Maybe. What number is MCC? What else is MCC? It's MC squared. So where's the half? Here is one half. Here is the other half. Einstein's energy equals mass times the speed of light squared. You see how I like to bury in my little riddles? No one's ever got them all. So you all can have fun with that. It's going to end soon at 6 o'clock. You all going to go have a beer or a glass of wine. That can help you to discover the other ones, okay? So let's go on to the end. Oh, there's more. There's more. And here I'm at the end. You have reliance on science, and then you add engineering, you can have a future endearing, but only if you have a culture-caring society. Embrace variety. Nature you have to respect every aspect. So if you keep cutting down the Amazon, you won't have a future. That's my message. So, conclusions and dreams. Now look, I'm at the other end of the beach. Still good looking. Very sweaty. So the final conclusions and dreams for my little talk here is nature, physics, and economics, and wide open eyes and minds. So this is the culture aspect of this, right? You creates opportunity. You combine it all to feed the economy and the people. And policy, if you move in a good direction, that means if you have better access to education, basic necessities, you will create a new skilled workforce that will enable you to build the robotic systems to make the solar panels right here in Brazil. And from that, I say, learn from China. Study what China did to go from a very low-skill, uneducated population with living in dirt floors with no electricity. How did they take and transform their society to be the world's most foremost manufacturing economy? A lot of those peoples who were poor and with nothing now, okay, maybe they work in factories and the people say, well, that's not as good a life. That's debatable, discussable, but that means that you can discuss it, fix it, and make it even better, is my hypothesis. And what you sow, you can then reap. So here's reap for the name of the conference. See, here was another little riddle I buried in here for fun. Okay? That's it. And I'm on time. It's 1:50. I have 2 minutes left. Any questions? Everybody wants to go have a beer. All right, class dismissed. Oh, no, you had a question. No, yeah, it's going to the bar. The future, you guys are the future. So, take it out and do great with it, okay? Have a great day.